The Engineering Equation Solver, better known as EASE, is a program that has been developed by Professor Sandy Klein at the University of Wisconsin-Madison. At its heart, EASE is an equation solver, and by that I mean that if you give it n equations with n unknowns, EASE can give you the solution. So if we go on and start looking at this, in order to enter equations, of course you need to type them somewhere, and that is the equation window that I'm in right now. So if I give it a simple set of equations, so x plus y is equal to 6, and 2 times x plus 3 times y is equal to 2, I've got 2 times x. I've got now two equations, two unknowns, x and y, and these two equations correspond to lines in Euclidean space, and the solution to that set of equations will exist provided the lines intersect. If I come to calculate and hit solve here, indeed the calculation has converged, and the answer is that the intersection occurs at x equals 16 and y is equal to minus 10. So that's all good and well, but if we go ahead and make this a little bit more interesting, so let's say these are no longer just simple linear equations, so x squared and y cubed, and instead of 3 times y, let's say 3 divided by y. Now we've got two complex curves in Euclidean space, and again, as long as they intersect, we'll get a solution. We hit solve, and indeed we have a solution, and there's our intersection point. And this will work up to a much larger number of equations than we have here, and there are several other software packages that will do similar types of things. The previous example was an excellent primer on using EASE as an equation solver. However, the real power of EASE is that EASE has built into it thermophysical properties that allow you to iteratively solve for thermodynamic quantities, which would mean in the process they will be updating the thermophysical properties. So let's look at a simple little example problem, and in the process of going through that, many of the main features of EASE will be experienced. The diagram window here is another feature of EASE that you can draw pictures and the like in this window. The problem, sample problem that I want to look at is a fairly straightforward problem. It involves a tank here, which is initially full of air. The tank volume is 1 cubic meter. Initial mass of air in the tank is 1 kilogram, and the tank is initially at 300 Kelvin. It is hooked up through a valve to a pipe which contains helium at the temperature of 300 Kelvin, a pressure of 2 megapascals. The problem here is that the valve is going to open, 1 kilogram of helium will be added to the tank, and the question is to find the final temperature in the tank. Okay, and the solution is fairly straightforward. I've written it out here for you. The change in internal energy, so this is just the first law of balance for this problem, is equal to then the added mass times the enthalpy. And the change in internal energy is the mass in the tank at state 2 times its internal energy minus, of course, m1 u1. The mass added is m2 minus m1, and the enthalpy is h. So if we go back now to the equation window, we can go ahead and start to solve this problem. So let's start with what we know. We know that the initial temperature T1 is 300 Kelvin. The mass of air in the tank is equal to 1 kilogram. The mass of helium that we're adding is 1 kilogram. The temperature in the line is 300 Kelvin, and the pressure in the line is equal to 2 megapascals. Well, I've gone through very quickly and entered these numbers, but there are units associated with these numbers as well. EASE is going to look up these thermodynamic properties for us, so we need to make sure that we're consistent with our units. So if we come up here to the options pull down and go to the unit system, let's check what unit system we're working in. Well, first of all, we're in SI units, which is correct. Here we're clicked currently in Celsius as the temperature unit. However, as you see, we've been working in Kelvin, so I want to change that. The energy is going to be in kilojoules. The properties, the specific properties, are going to be on a mass basis. We're given the mass of air and the mass of helium, so that's good. The pressure units here are in terms of kilopascals, and so it is important now that we know that, so that when we put in our pressure of the line here, we've got that correct. And so let's OK. Of course, there's a syntax error there. The pressure in the line is now 2,000 kilopascals. The tank volume is 1 meter cubed, and those are all of our, if you will, known values. The unknowns that we need to work with are the internal energy, for instance, of all the different, both the different species, the enthalpy of the helium. And so if we go ahead and define a variable use of air at state 1, that would be the internal energy of the air in the tank at the initial condition. We need some expression for the internal energy, and here is where ease is functionality is at its best. So if we come back to options and function info, we see math functions, the standard different types of math functions down here, but there's also fluid properties. And if we come down, we see a whole list of different fluid properties here: thermal conductivity, specific heats, density, enthalpy, and a whole bunch of different fluids over here. So we are looking for the internal energy of air. So if we come down here, we find int energy. That's the function call. The fluid that we're interested in this case, is air. And we see then that the function call to give us the internal energy is int energy of air t equals some temperature T1 here. So if we go ahead and paste that, we're all set. And so the nice thing, just coincidentally, is that my initial temperature was T1. So indeed, we're going to look up the internal energy for the fluid air at T1, which in our case is 300 Kelvin. Well, we also have to know the internal energy of the air at the final state. And so we go ahead and put that in. And now, what's the final temperature? Well, we don't know, and in fact, that's what we're trying to solve. So we can enter that as a variable here in the function call for internal energy. And when ease goes out and solves for T2, it will continuously be updating this value of internal energy, and the final solution we get is then going to be consistent. And so that is the real power of ease, is that it can iterate the variables in these function calls here. We also need to know the internal energy of helium at state 2. And so again, if we come up here to our function info, internal energy, we can now scroll down and look for helium in this list, and we get helium. And we see here that the function call now looks the same. Of course, internal energy, we've got helium, but now we have to give it both a temperature and a pressure. So let's paste that in. And the reason we need to specify both the temperature and the pressure is that helium is treated as a real gas in ease, and so so the internal energy isn't solely a function of temperature. We're trying to evaluate this at the final state, so that would be at T2, and also at the pressure P2. The other thermophysical property we need is the enthalpy of the helium as it comes from the line. Again, if we come to the function info, we can now click on enthalpy, and again we have enthalpy of helium, T equals T1, P equals some pressure. The temperature that we want to know the enthalpy of helium at is the line temperature, and the pressure is the line pressure. Okay, and so now we've got all of our thermodynamic properties. We're ready to go. Well, what are our unknowns at this point? We have T2, which is unknown, but we also don't know P2. And so what we need to do is we need some way to relate P2 to T2, and that relationship is going to be from the ideal gas law. So if we have P2 times the volume, that will equal the number of moles at state 2, let's call it N2, times the universal gas constant, which I'll call R sub U, times T2. Okay? Now N2, as I said, is the number of moles at state 2, and so that is going to equal the mass of the air divided by the molecular weight of air. And if you don't remember the molecular weight of air, we can go back here to our function info and go to molar mass and air. Okay, so that would be the number of moles of air in the tank, and then we have to add then the same thing for helium. So the mass of helium divided by the molar mass of helium. So scroll down to helium, and we're set. We have introduced another unknown, which is the universal gas constant, which I will put in then. So Ru is 8.314 kilojoules per kilomole Kelvin, and we're going to come back to these units in just one moment. But we still need one more equation to solve this problem, and that is the first law balance that we saw in the diagram window. So if we look at the state 2, right, it would be the internal energy at state 2, which is the mass of air times the U of air at 2, plus the mass of helium times the internal energy of helium at state 2, minus now the internal energy at state 1, which was just the mass of air times the internal energy of air at state 1. And that is going to equal the mass that's been added, which in our case is the mass of helium, times the enthalpy of that, which is the enthalpy of helium. Okay, ease is not case sensitive, but just for consistency reasons, I choose to make it all the variables look the same. Okay, so in principle, we should be able to solve if I haven't made any typing errors. But before we do that, it's important that we address this units issue a little bit more fully. So if we come to the options and we now go to variable info, and this is going to tell us information about the variables in our problem, we get here the list of the variables in this column. Then there are guess values, and the guess values are used because the way equation solvers work is you guess a value and then you converge onto the solution. So you always have to have some starting point to work from. So the guess values are just set to 1 automatically in ease. You can also specify limits, meaning a lower and upper limit for these variables in ease. And then at the final column here are units. And so the properties, the enthalpy here and the internal energy down here, automatically have the units associated with them, but the other parameters don't. And it's very useful because ease will do a unit check, and often that is one of the biggest causes of problems. So the mass of air is in kilograms, mass of helium in kilograms. The number of moles is kilomoles. Pressure is in kilopascals, and oops. We've got that. The universal gas constant is in kilojoules per kilomole Kelvin. Temperature is in Kelvin. And finally, the internal energies here are in kilojoules per kilogram. And then the final thing here, the volume, is in meters cubed. Okay, so now we've got our units set, and we should be, in principle, be ready to see if we can solve. So if we come to calculate and solve, we get an error message. And it says here that the temperature is out of the range, and the allowable range being 2.177 to 1500 Kelvin. And so the issue here is that we are outside of that with our original guess value. So if we go back now to the variable info and we look at this, our initial guess for T2 is 1 degree Kelvin, okay, which of course is not realistic. So let's just put in 300 Kelvin as a starting guess here and see what happens. And if we go ahead and hit solve here, indeed we have a solution, and when we go and we look at the solution, we see that the final temperature that it returns is 463.8 Kelvin, and in that same process we've solved for the final pressure P2. That works out to be 1097 kilopascals. So EASE has given us a solution. The solution is consistent with everything we know, meaning that the flow work associated with this helium coming in causes the temperature in the tank to rise. And further, we look down here at the bottom, and the solution tells us that no unit consistency or conversion problems were detected. And so by using the units in EASE, it has gone through and checked everything out. Okay, so now that's a nice example, but what if, for instance, we did not know the mass of helium that was coming into the system? Or, let me say it another way, what if we wanted to know the temperature as a function of the mass of helium that we were adding? And EASE allows us to do that as well. And so let's go back into the equation window, and I haven't shown this to you yet, but EASE, you can comment lines out of EASE by using the curly brackets. So if we put a curly bracket at the front and the end there, now we have not specified the mass of helium. But what we can do is we can make what's called a parametric table in EASE. So if I go to Tables, New Parametric Table, I get the choice of all the different variables that I want to put in the table. So for instance, I want to have the mass of helium be a variable, so that's going to be part of this table. And let's say I want to monitor the pressure P2 and the temperature T2 as a function of the mass of helium that we add to our tank. The parametric table is going to be set up to have 10 rows or 10 different runs, and it's going to be given a name, just table 1, which is fine for this example. So we hit add, and now our table will have those 3 variables in it. So here's then our parametric table, and we've got the mass of the helium, pressure, and temperature. What we need to do is we still need to specify one more parameter in the problem, and in particular we're going to specify the mass of helium. So if we click in the upper right hand corner here, we get this menu which allows us to actually change the values of helium. I could alternatively have just written the values in by hand, typed them in by hand. So let's say the first value is going to be 0.1 kilograms. The last value I'm going to have is 1 kilogram. Okay, and I hit OK, and it automatically fills in those columns. And so now I want to solve for each value of the mass of helium in this table. And to do that, I come to the Calculate, and now I go to the Solve Table option and click OK, and it went through and now solved for this. So as I add the helium mass from 0.1 to 1 kilograms, the temperature goes from 361 Kelvin up to 463 Kelvin. And the EASE has features for plotting, so we can go to Plot, New Plot Window, to an XY plot. The plot name is just going to be Plot 1. The data is going to be coming from the parametric table, and in particular table number 1, and of course we can then choose what's on the X and the Y axis. So if the X axis is the mass of helium, on the Y axis we can put temperature. There are a number of different options here which you can play with, but let's hit OK, and we see then the plot of temperature as a function of the mass of helium. And so this gives you some ideas about the power of ease. The main thing that's important is the ability to navigate between these different windows. Of course, you can do that simply through the Windows menu at the top. So for instance, in some problems that you'll be working, there'll be data in the parametric table that you might want to get at directly. So you want to look at the raw data directly. Other places you might want to be looking at the plots directly, and so you can navigate between those.